Welcome everyone to the 2026 Integrated Photonics Summit. Thank you all so much for joining us, and in this session you'll hear from Michael Geiselmann, the President and Chief Commercial Officer at LIGENTEC. Michael studied physics and engineering, earning his doctorate at the Institute of Photonic Sciences in Barcelona. Today he joins us to discuss heterogeneous integration on a silicon nitride platform to bridge the gap between photonic performance and industrial viability. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch them on demand. That's all for me. Michael, it's great to see you again, and we appreciate you for taking the time to join us here at the Integrated Photonics Summit.
Thank you very much, Jacob. I'm happy to talk about today scaling the next generation optical engines, and I will particularly talk about heterogeneous thin film lithium niobate integration on low loss photonic integrated circuits. Feel free to always reach out at info@ligentec.com to discuss your projects. LIGENTEC's mission is to unleash the potential of photonic integrated circuits, or in short, how we call it, let's pick it. We want to put PICs in products that are very critical and need integration, for example, satellite communication, but also into products where the volume and the price is driving photonic integration in high volume markets. LIGENTEC serves customers in the three different pillars: sense, connect, and compute. In the sensing pillar, we have everything from biosensing to sense biomarkers, to OCT or LiDAR to measure distances, to metrology and instrumentation, and more positioning and navigation. For example, atomic clocks and GPS-less navigation. In the connect pillar, we have DCI and coherent fiber optics, and satellite communication, optical circuit switching, and quantum key distribution as one of our customer applications. In the compute part, we serve customers for quantum computing, neuromorphic computing, and optical I/O and interposers for artificial intelligence and data centers. LIGENTEC is headquartered in Lausanne in Switzerland, but we have offices and subsidiaries in France, south of Paris, and in Belgium, in Ghent, and then we're a bit more than 80 photonic enthusiasts that serve our customers with the best-in-class photonic integrated circuits with losses down to below 0.2 dB per meter, with 3 technology offerings for different wavelengths and different applications. And today I will focus on the integration with actives and the related PDKs with that. LIGENTEC is a solution partner with a core expertise on fabrication of photonic integrated circuits, which is happening at LIGENTEC and X-FAB. And we also have a team of experts and photonic integrated experts to do a feasibility study where you can come with your idea and we can help you get your design and layout together so you can fabricate your photonic integrated circuit. We have also certain measurement capabilities and work with packaging partners in the ecosystem to provide you a fully packaged PIC. So you don't need necessarily to have your own fiber measurement positioning devices, but of course we can also serve you with only photonic integrated circuits without packaging. We have a strategic partnership for volume production with X-FAB, and this is why we're located in the south of Paris. Our offices are on the campus of X-FAB in Corbeil-Essonnes, and here we have access to a 200 millimeter clean room facility that is used for CMOS fabrication, and we have transferred a process that we initially developed more than 10 years ago to that 200 millimeter CMOS fab. So we have that best-in-class silicon nitride, but it's a passive material. In that we developed over the last 10 years comprehensive PDKs and very good passive components with good I/O, and we showed scalability to volume. And now we're integrating active components to address detection, modulation, amplification, and laser integration. And here we're looking at different materials, and one key material that I want to talk about today is thin film lithium niobate. So the low losses in silicon nitride passives, we have them in three different platforms. Why do we have three different thicknesses? These address different wavelength regions for different markets, and the process modules, you can stack different nitride layers, you can integrate heaters, you can integrate the local cladding opening, which is glass, to get access to the evanescent field of the waveguide, to have other materials interact, or in a biosensor molecules interact with your waveguide. That is all established within a process design kit, where we do full automated wafer testing to get statistics of the different components. So we have propagation losses that can go down to 0.2 dB per meter, coupling losses that are below 1 dB per fiber to chip coupling, but we have even demonstrated much below 200 millidB. Optical crossings are in the range of 10 millidB, and the thermal phase shifter 15 millidB, and polarization extinction ratio above 30 dB. So these losses are obtained not on a single chip, but on a cross wafer. So we have here on the top, we see three different 200 millimeter wafers with the statistics of the optical losses based on cutback structures that give us around 4 dB per meter in 1 micron by 350 nanometer wide waveguides, and we can also go down to 0.2 dB per meter loss in a wider waveguide. The coupling of the fiber to a chip is below 1 dB, and we are working on solutions to get even lower than that in C and L band, but also in other bands like O band down to the visible, where we have reached coupling losses way below 1 dB per facet for SMF fiber. One low loss modulation or phase shifter integration is a heater where the waveguide does not interact with the heater material, and so the losses are not influenced by the heater material. And here we have a structure that can reach very low pi phase shift powers down to 15 milliwatts, keeping a speed of kilohertz for the switching speed in these efficient thermo-optic phase shifters. And one application that we can do with these excellent passive components is for example, a tunable narrow line width laser, where you integrate a 3-5 component like an RSOA together with a silicon nitride circuit and the heaters that act as phase shifters and tunable elements for the cavities. And with that we can reach kilohertz with maximum power outputs of tens of milliwatts and tuning ranges of tens of nanometers. But what is missing in a low loss platform is a high speed modulation approach, and here we're looking at thin film lithium niobate. So we're starting from a low loss silicon nitride wafer and integrate thin film lithium niobate on top of the silicon nitride waveguides that allow for low loss RF modulation. And how does that look like? So you have here in the blue, you see waveguides, several waveguides. The edge coupling comes from the top. You see waveguides that then have a splitter and that go into several Mach-Zehnder interferometers, and only the straight part with the green is in lithium niobate, and the golden part are the electrodes of the lithium niobate. And afterwards, your edge coupler is going out again from the lower bottom right part of that chip. So we have that heterogeneous integration platform, and that combine a mature silicon nitride platform with electro-optical material. We use our advanced nitride technology that is established since many years and running in a 200 millimeter CMOS line, together with lithium niobate technology to create an hybrid mode between the nitride and the lithium niobate. That is definitely happening in a different line. So lithium niobate is not allowed in a CMOS line. So the integration of lithium niobate is happening in a different line. So here we see the integration example of nitride plus lithium niobate and the different components that we're using. We start with the edge couplers on the left hand side, then go to the 2x2 MMIs, and then these split and go through the RF electrode. And on the bottom we have path length difference in the Mach-Zehnder interferometer, and go to a vertical transition from the nitride into the hybrid mode from consisting of nitride plus lithium niobate, and then also have a bias control integrated on the lithium niobate chip. The advantages of this hybrid integration approach is that only the essential components in thin film lithium niobate are used, meaning the modulation part. All other components remain in silicon nitride, where all the standard building blocks from the PDK of silicon nitride are available. The modulation specifications can go beyond 110 gigahertz with PICs in the range of 2 volt and extinction ratios beyond 35 dB. That hybrid mode approach gives us the opportunity to have a very low propagation loss, so we can transfer the low propagation loss from nitride into that hybrid mode with a simplified fabrication approach, and have the escalator loss and the fiber to chip coupling much to the overall losses, so you can get in the end a fully packaged modulator with fiber to fiber losses below 2.5 dB. Also, we have the measurements of the Mach-Zehnder interferometer that clearly show extinction ratios beyond 35 dB, and impedance matching to a 50 ohm on chip termination. The high-speed modulator can thus be used in integration schemes where we want to have a transmitter device and modulate that at high speeds up to 120 gigahertz. But you also want to have photodetector integration on the chip itself, and here we address the on-chip photodetector integration with an approach of microtransfer printing, and that is also a wafer level approach to get 3.5 components on the low loss silicon nitride chip itself. How does microtransfer printing work? So we have a 3.5 source substrate with prefabricated PDs, and these PDs need to be fabricated in a certain way that they are only held by a tether structure, and then a stamp comes and picks up the PD by pushing it down. It breaks the tether, and then the PD is on the stamp and will be printed on a silicon nitride target wafer. And with this approach, there is the advantage that you have pre-characterized PDs on your 3.5 source substrate, and you can use that technique as a volume fabrication technique to get PDs that of your choice to a very low loss nitride target platform. And key specifications of the current technology is that we have 140 femtofarad junction capacitance and above 10 gigahertz bandwidth, and the bandwidth is mainly defined by the source substrate of the PDs. So you choose another source substrate of the PD. So you choose another photodetector, and you can then integrate photodetectors that are also with much higher RF bandwidth. So the material you pick in the end for the microtransfer printing is the choice of your specifications for the photodetector, and so you can get a very high responsivity, and you connect your PDs with a second metal structure that we have in our platform. Last but not least, we also have gain. We're working on gain integration on our low loss platform. So we have our silicon nitride photonic integrated circuit where then in a collaboration with University of Ghent in the CSOC project, we print SOA with transfer printing on the silicon nitride waveguide, and demonstrate lasing in C-band with that technology approach. That is an overview of the whole laser architecture. So we have a whole laser, a tunable laser, where we transfer print the indium phosphide based gain and the gallium arsenide based gain onto the silicon nitride waveguides to achieve a gain in different wavelength region for C and O band. With this, I would like to thank you for your attention, and I'm happy to get in contact with you through info@ligentech.com and answer any possible questions.
And thank you, Michael, for sharing how to scale next-gen optical engines and address the gap between photonic performance and industrial viability. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Integrated Photonics Summit. Thank you all so much for joining us.